Next, we're going to translate the slope of a tangent line into parametric equations. When it came to slope of a tangent line, we frequently referred to this as the derivative dy over dx, to be representative of the fact that this is really the limit as delta x approaches 0 of delta y over delta x. That is the limit as the change in x goes to 0 of just our standard slope formula when it comes to 2 points that are on a line. Now, every time that we've done this, we've operated under the assumption that y has been a function of x. What we're going to do now is operate under the following assumption. We're going to assume that y is going to be a function of t. We're going to assume that x is now a function of t as well. We can still make this assumption, that's okay, but that just means that we're going to wind up with a composition of functions, which is that y of t is going to be equal to y of x of t. Now, it's because of this that we're going to be able to come up with a very different kind of derivative on the right-hand side. This will require extensive use of the chain rule. So if I were to say, let's take a derivative of both sides, the independent variable that I would be using would be t. So we'll apply d over dt to both sides. On the left-hand side, this will be a very straightforward dy over dt. On the right-hand side, this is where we're going to see the chain rule take place. We differentiate the outside function with respect to the inside function, and then multiply by the derivative of that inside function. Now, technically speaking, though, the thing that we're interested in solving for here would be this dy over dx. So what I'm going to do is have us solve for dy over dx. By solving for dy over dx, this will give us a formula for how to find the slope of a tangent line in parametric equations. So take our dy over dt and divide by dx over dt. This winds up giving us a formula for the slope of a tangent line in parametric equations. However, there are a couple of special things that we can take out of this. Special things. So first, a special thing that we can get out of this is if dy over dt is equal to 0 and dx over dt is not equal to 0, then this fraction would take the form 0 divided by something that's not 0. Now that would give us a slope of a tangent line of a horizontal line. That would just be 0. However, we can also think of this as y is not changing while x is changing. Y is not changing while x is changing would be exactly a horizontal line. So we'll point out the tangent line is horizontal. Or you could simply say that the slope of the tangent line would be 0. Now this extends nicely if we were to also consider dx dt being equal to 0 and dy dt being non-zero. Now, in this case, what we're saying is that we have something that's not 0 divided by something that is 0. Unfortunately, that's undefined, and the kinds of lines that have an undefined slope are vertical lines. We can also think of this as saying x is not changing, but y is changing. And in this case, if x is not changing, but y is changing, you have yourself a vertical line. The tangent line, there we go, is vertical. Now the other thing would be to point out that if dx over dt is equal to 0 and dy over dt is equal to 0, we can draw no conclusion. Now if, just as an example, y and x are both functions of t, and this represents the motion of a particle around some plane. What this would mean is that the particle has come to a full stop. It is moving in neither the y direction nor the x direction. Now what could happen is it could just continue moving in the same direction before it stopped. It could also turn and start moving in another direction. The thing is, we're not able to draw a conclusion about this if both of them are equal to 0. We will encounter at least one case of this before the end of the chapter. Just wanted to make you aware of it. The other special thing that we're going to be able to take out of this that'll be especially relevant in the next video is that we can now conclude that if we're taking the derivative with respect to x of something, this is the same as saying take the derivative of that something with respect to t and then divide by dx over dt. So essentially take whatever's in the numerator and in the denominator and differentiate both of them with respect to t. You know what, I did say next video, we'll just go ahead and define it now. A second derivative for concavity. Concavity is defined as d squared y over dx squared. But really that's just a fancy way of saying take the derivative with respect to x of dy over dx. So with that in mind, if we apply this mindset that we had back here of take the derivative with respect to x of this thing and apply this formula, we can conclude that this will be the derivative with respect to t of dy over dx. That is what we got back here. That'll probably involve using the quotient rule, divided by dx dt. We'll see in the next video a couple examples of making use of these formulas for the slope of a tangent line as well as concavity.